Recording. Okay. Good evening, everyone. Please confirm again that you can see me and that you can hear me properly as we commence. Hi.
Yes.
Okay, thank you so much. Thank you. So my name is Iveren, but you can call me Ivy for short. I'll be the host for today's event. We will try as much as possible to keep this as short as possible because we know it's Saturday and everyone would like to rest and get on with other activities. So, like I said, my name is Iveren. I'm one of the experts at the Advancement for Artificial Intelligence, the Nigerian chapter. Yes, I serve as the Director for Learning and Engagement, and I'll be your host for today. So, without wasting much time, I'd like to introduce our speaker, who is in the person of Mr. Noah Ayodeji. He's a seasoned technology leader with over 16 years of experience across the digital technology landscape, including applications development, cloud engineering, data platforms, and AI driven solutions. He currently serves as a senior applications developer at Fujitsu America Incorporated in Canada, where he leads the design and integration of landscape enterprise grade applications. He holds several industry recognized certificates, including Microsoft Azure AI Engineer, Azure Data Scientist Associate, Azure Developer Associate, and AWS DevOps Engineer Professional. And this demonstrates deep expertise in modern cloud architecture and intelligent systems. Mr. Noah has earned his undergraduate degree in electrical engineering from the University of Ilorin and holds an MBA from Lagos Business School, as well as a Master's of Management in Innovation and Entrepreneurship from Queen's University, Canada. His work sits at the intersection of technology, business strategy, and innovation, equipping organizations to build and scale impactful digital solutions. And he's here today to share his wealth of knowledge with us. If you are as excited as I am, please put your hands together for him. Um, Show celebration however you can, using any emoji you can. Just show that you are happy to be here and you're happy to have this enigma sitting right in front of you. Welcome and thank you so much, Mr. Noah, for sharing your time and your knowledge with us today. The floor is yours.
Oh,
And
thank you, Ivy. That was an amazing introduction. Yeah, that was really nice. Thanks a lot, and thanks for having me. I'll just go ahead now and share my screen.
okay.
Okay. Yeah. I hope everyone can see me. Can you see me?
Yes.
Okay, but can you see the screen now?
Okay. I think I should stop sharing so that you can share.
Okay. Is it? Yeah, I should. Yeah, can you see my screen now? Can everyone see my screen?
I think it's still loading. Yes, we can see your screen.
Okay. All right, good. So, today, that was an amazing introduction, and thanks for that. I feel very elated. And yeah, so today we'll be talking about, from UI to integration, engineering scalable React applications with REST APIs. I know this is a technical, topic, and I'll try as much as possible to bring it home so that a lot of our non-technical audience will understand what we are talking about. So what is this session about? Today, we're going to be exploring how modern applications are built. And it's not just by showing you complex code. but by showing you the thinking behind how developers design software that works at scale. We're going to use analogy that everyone knows: building a house. So what you will learn today is how software is designed like a building, from foundation to finished product. I'll also be introducing you to a topic called atomic design, which is a smart way of building user interfaces using small reusable pieces. I'll be talking about REST APIs, how different applications talk to each other, like how buildings are connected by roads. Then I will also be talking about scalability, how to build software that grows without falling apart. And who is this for? So whether you're a developer, a tech enthusiast, a student, or someone curious about how applications and websites are built behind the scenes, this session is for you. We're going to keep things visual, practical, and jargon-free wherever possible. And the big question we'll be answering today is, okay, so imagine you want to build a house. You wouldn't just start stacking bricks randomly, right? I mean, you are going to plan how you're going to lay the foundation, whether you're going to build it room by room, or you're going to connect it to water, electricity, or roads. So in the same way, building software works the same way. And today we are going to show you how. So yes, firstly, let's think like a builder. So before we touch any technology, let's establish the mental model that will guide our entire conversation. So building software is like building a house. And once you see the parallels, everything about application design will make more sense. So here's the big idea. Software is like a building project. Every software you use, Instagram, WhatsApp, your banking app, was built in the same way a construction company builds a house. So there is a plan, there are materials, there are structures, and there are connections to the outside world. So it's like building a house is you have the blueprint, the foundation, the walls, the rooms, the plumbing, the electricity, roads to other places. And then, build it's like building an app as well. You have the design system, you have the project setup, the components, the features, the data layers, the APIs to other services. And why does this matter? When you understand that software follows the same logic as construction, you will understand why developers make certain decisions. So a sloppy foundation, for example, means that the building will crack later. So when you don't plan the building properly, it won't grow. Adding new floors, new rooms without tearing things down. So that is why this matters. And when you look at the foundation, before any visible structure appears, the engineers test the soil, they pour the concrete, they lay plumbing and electrical conduits underground. I mean, this is visible to the people who live in the house, but without heat. Sorry, that is very invisible to the people who live in the house, but without it, nothing above ground would work. So in software, before any user-facing feature is built, developers like us, we set up the project structure, how files are organized, what tools are used, how the application will handle data, and what rules the code must follow. Users will never see this, but everything depends on it. So in construction, you have your soil testing, right? So in software, what we do is we choose the right tools and frameworks. And then in construction, you pour the foundation. In software, we set up the project structure. In construction, you lay the plumbing underground. In software, we configure how data flows in the app. In construction, electrical conduits are made in the slab, right? In software, we set up connections to external services. In construction, you follow building code compliance. In software also, we follow code quality rules and standard. So I move on to still talking about the foundational aspects of software building, I'll move on into the room analogy. So in construction, a kitchen is for cooking, right? A bedroom is for sleeping. A bathroom is for bathing. I mean, you don't cook in the bedroom and you don't sleep in the kitchen, right? Because each room has a single clear purpose and they are connected by the doors and hallways. So in React applications, we build components. So small focused pieces of the interface that each does one thing. Sorry, that each do one thing. A login form handles login. A navigation bar shows the menu. A profile card shows user info. So they don't overlap. Each one has its job and they connect to each other through data. So, and just like rooms are grouped into floors, ground floor for living, first floor for bedrooms, components are grouped into features. So an authentication section, for example, a dashboard section and a payment section. These are kind of like features. So the key principle here is that the smaller and more focused each room is, the easier it is to renovate one room without demolishing the entire floor, right? So the same is true for software components. And then we talk about the estate. So from one building to many. So once you have one building, you might want to expand into an estate, multiple buildings, shared roads, main gates with security, a power supply station, a water system. Each building is independent, but they share the same structure. So as an application grows, it becomes a system of connected parts. Different features become like different buildings. They share common services. Authentication, for example, is like a gate. Data management is like the power supply. And API connections are like, the roads connecting to the outside world. So you have in software, you have the login system checking who is allowed in. That's like your gate. You have the service layer in the software, which is like how features communicate. So that's like roads connecting buildings. We also have data management. We have caching, which is like your water supply. We have global settings. So things that things that affect the whole application. So it's like the estate management office, central office, where you have, when the entire coordination is happening. All right. So that's like the global settings in an application as well. And then we have APIs, connecting to external services. So roads to other estates. So that's the way it is. And then the user experience. So think of it like a park, right? So a park is designed for people who use it, right? So nobody visiting a park cares about the drainage system beneath it, or how deep the electrical cables for the street lamps are buried, or they only care that the park works, the lights are on, and the paths are smooth. So in the same way, in software, users of our applications don't care about how we structure our code. They just care that the application is fast, it works, and it doesn't crash. So everything we have discussed, talking about the foundation, the rooms, the estates, infrastructure, exists so that the person using the app has a smooth, seamless experience. So, and that's the goal of all this engineering. The user should never have to think about the engineering. If they do, then something is wrong, right? So yeah, and let's move on to atomic design, because this is one of the principles we use. So now that we understand the building analogy, let's talk about how we actually construct the rooms, the floors, and the walls of our software building. The method is called atomic design, and it's surprisingly similar to how construction materials work. So what is it? So atomic design is a method for building user interfaces by starting with the smallest pieces and combining them into bigger and bigger units. By the way, atomic design that I'm talking about, that I'm using to explain this, it's just one of the principles of design and component architecture in our application design. So this is just one of them. It's a whole lot of information when speaking about application architecture and all of that. But I've just picked this particular, topic, so you can relate. So I can explain it, in a very easy way. So atomic design is a method for building user interfaces. So it was created by a designer called Brad Frost, and today it's become uh, a mainstream in application development. And it borrows the idea from chemistry. Everything in nature is made up of atoms, combining to form molecules, which also combine to form organism. So think of it this way: a brick on its own is small and simple, but when they combine together, you get a wall. When you combine walls, you get a room. When you combine rooms, you get a floor. When you combine floors, you get a building. So that's the same way atomic design works, but for software interfaces. So you have 5 levels, the atoms, smallest pieces. So a button, for example, when you press that transfer button on your banking application, that's an atom. So a text label and an input field. You also have molecules, small groups of atoms working together. For example, a search bar, which has an input and a button together. And then you have organisms, uh, which is complete sections made of molecules. You can have a navigation header with logo, menu, and search. Then you have templates, page layouts showing where organisms go, like a floor plan before furniture. And then you have the pages, which is like, the real life products, templates filled with actual content and data. So, you have it that way. And then, so we have atoms, like they're like bricks. I've explained this, where you have brick, nails, and screws. So these are kind of like the most basic construction materials. And then why do they matter? They matter because if all your bricks are the same quality and standard size, then every wall you build will be consistent. So in software, if you design your atoms very well, like having consistent buttons, consistent textiles, consistent colors, then everything built on top of them will automatically look and feel consistent. So think about every app you use. Notice how all the buttons look the same. The blue send button in your email app and the blue post button on your social media. That consistency comes from well-designed atoms. So we're talking about molecules. A wall frame, for example, a window frame. So bricks are, combined with cement forms a wall. Wood pieces combined form a window frame. Small groups, with clear purpose. So it's the same way, like a search bar in software, where you have an input plus a button. So you have a label plus an input and an error message. That forms a form field. So that's the same way 2 or more atoms coming together forms a molecule. So, think of it this way: a wall is just bricks and cement, right? But once you have a wall, you can use it anywhere. A kitchen wall, a bedroom wall, a fence wall. You don't reinvent walls each time. So the same way we have in software, once you build a search bar molecule, you can put it in the header or on the project or on the products page or in the admin panel, everywhere without rebuilding it. That's the way it works. And then you have organisms, which I will just I'm using analogies here so it's easy for everyone to follow and understand. Uh, Organisms are like rooms. So you have walls, you have doors, you have windows, you have ceiling, you have floors. That makes a kitchen, right? So it's a self-contained functional space. The same way in software building, we have logo, menu, search bar, profile icon. That forms your navigation header. So it's a complete reusable section of the interface. And why does it matter? because organisms are where your building starts connecting to the outside world. So a kitchen doesn't just exist on its own, right? It needs the water piped in from outside, the electricity connected to the grid, and the gas supplied by a provider. So these are the room's connection to external services. In software, this is exactly where components start talking to APIs, fetching data from a server, sending user input somewhere, displaying live information. So, I mean, here is a key insight. An organism, like a room, doesn't need to know how the water gets to the tap. It just needs to know that when you turn the tap, water comes out. So in software, a component doesn't need to know how the API works. It just asks for the data and displays it. So this separation is what makes everything manageable. And then you have templates and pages. So this is the live application itself. The layout is filled with real data. Real users are interacting. Everything is functioning. Uh, and then why all this matters? I mean, you build a wall once. We're talking about usability here. You build a wall once, you use it in every room. You build a search bar once, you use it on every page. It's also very important for consistency because when all your bricks are the same, every wall looks professional. When all your buttons are the same, your app looks polished. It's also good for maintainability. You need to change the color of all buttons. You just need to change the atom once and it updates everywhere. It's like painting all bricks the same color before building. And then again, scalability. Adding a new room to a well-structured building is straightforward. I mean, adding a new feature to a well-structured app is the same. So just compose existing atoms and molecules in new ways. So here's the thing. Imagine you want to change the kitchen tap in a well-built house. You go to the kitchen, you change the tap, done. The rest of the house is unaffected. So now imagine a house where all the plumbing is tangled together with no plan. So changing one tap might affect the bedroom shower. And that's what happens when software isn't designed with atomic principles. So then we talk about the REST APIs. So this is it. With REST APIs, we are talking about how buildings talk to each other. So far, we've been focused on one thing, building one house, right? But in a real world, your house doesn't just exist in isolation. It's part of a neighborhood. It's connected to power, water, the internet, and other services. In software, these connections are called APIs. So what is an API? I'm going to use a restaurant analogy here. So imagine you're at a restaurant. You are the customer sitting down and looking at the menu. And the menu tells you what's available and how to order it. You tell the waiter what you want. The waiter goes to the kitchen and brings back your food. You never go into the kitchen yourself, right? You don't need to know how they cook. You just need to know what to ask for and what you will get back. In the same way, the restaurant, the menu is your API documentation in software. It tells you what's available. The waiter, that's your HTTP request, carries your order to the server. The kitchen, that's the server backend where data is stored and processed. Your table, that's your application where the results gets displayed. And your food, that's the response, the data you ask for. So an API is simply a set of rules for how two applications talk to each other. It defines what you can ask for, how to ask for it, and what you will get back. And that's it. So when you have uh, uh, applications working, they are probably talking out to different APIs. So let me just tell you what REST API is in plainly in English. It's called representational state transfer. And it's just a style of designing APIs. So think of it as a set of conventions, like how restaurants everywhere follow similar patterns. You sit, you order, you eat, you pay, right? So in REST APIs, you have some rules such as the get, the post, the put, and the delete. So the get, for example, will tell you, okay, that means show me the menu, bring my order. You are requesting information. Post is like, oh, I'd like to place a new order. So you are sending new information. That's what that means. Put is, oh, actually, change my order to this. That is, you are changing, you're updating existing information. And then delete, or cancel my order. You are removing something, right? So that's the way REST API works. And then you're building. So let's go back to our estate analogy. Your building, which is your React application, doesn't exist in isolation. It needs to communicate with other building, other services, and systems. So imagine your building is in an estate down the road where there is a bank. Okay, that's a payment service, right? And then you also have post office. That's the email service. Then you have the government office, authentication service. Then you have the warehouse, which is the database. You can see how I'm linking everything to software now. So your building is connected to all of these through roads. Those are the API connections. So when a user wants to make payment, your building sends a request down the road to the bank building, and the bank sends back a confirmation. So in the same way, you can think of, within the estate, the bank is, is like an external service. So in software, that is like Stripe, Paystack, Flutterwave, because they offer payment services. And when you are building a software, when you are building an application, you need that service, right? To be able to, so that your customers will be able to use their payment cards to purchase your products and all of those things. So that external service are like, Stripe, Paystack, and Flutterwave, those kind of providers offer that service. So that's it. And what it does, it handles payments. The post office, for example, within your estate building, the external service in software could be like providers like SendGrid, Mailgun. And what do? They send emails. So when a customer makes a purchase, they get an email confirmation, right? So that external service handles that, and they are connected to your application, connects to those external services through APIs. The government office, that's your Firebase authentication in software. And what does it do? It verifies identity. The warehouse, that's your backend and database in software engineering. And what do? They store and retrieve data. The map office, that's like your Google Maps API. It provides location data. So each of these external buildings has a gate, an API endpoint. They don't just let you walk into their building, right? You go to their gate, make a request, and they hand you what you need. This keeps everything secured and organized. So we talk about security. So in API, we have key concepts like API key. So it's like a permanent resident card, where you belong. Then you also have access token. A visitor pass, it's only valid for a limited time. You have rate limiting. The gate has a speed limit. You can't just rush in. You can't rush 100 people through at once. Then you have your CORS rules. That's the estate rule. Only certain gates can send visitors in. Then you have your HTTPS. That's your armored vehicle, so that your request travels safely on the road. So that's and then when things go wrong, these are some of the error codes in software engineering, API error codes. So sometimes the road is closed, right? Sometimes the building you are visiting is under maintenance. Sometimes you show up without the right ID. So in the physical world, you see a sign, you can see something like road closed or move this way. So that's what these error messages does. I'm sure you might have experience some of these error messages sometimes. You are trying to access a page and it's not showing, So that's exactly what happens. So when an API request fails, the server sends back a status code, which is a number that tells you what went wrong. So these are like signs on the road. So 200 means success. You arrived, you got what you needed, going home happy. 400, you asked for something that doesn't make sense. Error code 401 means unauthorized. You showed up at the gate without an ID. Error 403 means forbidden. You have an ID, but you are not allowed in this section. Error 404 is not found. The building you are looking for doesn't exist at this address. Error 500 means server error. The building has a problem, but it's again later. Error 429 request. Slow down. The gate says slow down. Too many visitors at once. So good software engineering handles this gracefully. So instead of showing users a scary error 500 message, they will show you something friendly saying, oh, we're having a trouble loading this right now. Please try again in a moment. So it's just like a park sign that says this part is temporarily closed. Try the other one. So stuff like that. So yes, now putting it all together, let's connect the dots. How does atomic design, which is our building method, how does it actually help when our building needs to access or connect to other services via APIs? And how does all of these make our application scalable? Atomic design plus APIs, I mean, this is where, imagine a kitchen and organism in a well-built house. The tap is a standard size atom. The sink unit combines, the tap basin and the drain, which is kind of like the molecule. The whole kitchen has a standardized plumbing connections, which is like the organisms. So when you need to connect this kitchen to the estate's water supply, which is like an API, you just connect to a single standard pipe, right? You don't need to replumb the whole room. Now imagine a poorly built kitchen where every pipe is a different size. Some go through the wall randomly and nothing follows a standard. Connecting to the water supply becomes a nightmare. You would have to tear things apart just to make a connection. So in software, when components follow atomic design principles, each organism complete section has a clean single point of connection to data services. The component doesn't contain messy data fetching logic spread everywhere. It has one clean pipe that brings data in, and the component just displays it. So it makes it easy to switch from one API provider to another provider. So it's like changing the water supplier. The kitchen tap will still work the same, right? So testing components without real data also helps because we can test the tap without connecting to the water supply. And then fixing API issues without breaking the UI. So we fix the pipe without demolishing the kitchen. And in terms of scalability, it also helps. So, think of it this way. A scalable estate is one that was designed so you can add more buildings without the whole estate falling apart. So if the roads are wide enough, the water supply can handle more connections. So you can build 10 more houses and everything will still work. The existing residents don't even notice the construction, right? But if the roads are narrow or the water pipes are too small, adding even one more house causes problems for everyone. So in software, we want the application to be scalable. And this is how uh, uh, multinational companies, the big tech companies build their applications. Facebook, Google, and all of these, companies, they build their architecture in a scalable way. A scalable application is one where you can add new features, handle more users, connect to more services without everything slowing down or breaking. So, and that's how atomic design enables scalability. So, so let's say we are trying to build, I just want to show you a real world walkthrough now as we wrap up. So let's build a user profile page for example. So let's trace through a real example to see all of this, in action. The first thing we want to do if we are going to build a profile page is to identify the atoms, the bricks, the avatar image, the text label, the button, the input field, the badges. These are the foundation, the basic building materials, the individual UI elements that exist in our design system. And then we combine them into molecules, like forming a wall. The avatar and the name label is like a user badge. The label input, the error text is like the form field. The button and a drop down is like the action menu. And then we build the organism. Now that we have the molecules, we can now have the user badge, the stats, the action menu to form a profile header. We can now have the form fields and the save button to form the edit profile form. And then the final step will now be, okay, connect to APIs. So it's like, plumbing to the estate. So the profile header now, needs user data. It needs a request down the road to your backend server, the warehouse. The server sends back the user's name, photo, and stats. The organism receives the data, passes it down to its molecules and atoms for display. So this is how it all works. And then you now have the full picture where you have a team members page, which is like, your template, where you have the user badge molecules, avatar, everything just coming together. And that's what makes it, scalable. It also gives it that level of performance, and it ensures that everything runs smoothly. And then, it just makes sure that the users never have to worry about anything. It ensures a good user experience. People using the application, are feeling good. The It's just like you have people in your head state. Users, they never think about the infrastructure. The lights just work, the water just flows, the roads are just smooth, and that's the goal. All right. So wrapping up, think the key takeaways is that you can see the journey we took today. We think like a builder. We talked about atomic design. We explained the concept of REST APIs. We put everything together, and then you can see how scalability, wins at the end of the day. And one thing you always need to know is that software is architecture. It's just like it's just like a building that needs blueprint, foundation, and structure. So that's the same way applications work. You have to build with small reusable pieces. So atomic design it's like starting small, combining into bigger units, molecules, and then you get a system that's easy to maintain and grow. And then APIs are like routes between buildings. REST APIs lets your application connect to other services. Good design inside your building, the atomic component, makes these connections cleaner. And then scalability is a design choice. It's not an afterthought. So when your building is well structured from day one, adding new rooms, new floors, or new connections to other buildings doesn't require tearing everything down. And yes, thank you. Any questions? Thank you so much.
Wow, wow. Thank you so much, Mr. Noah. It's one thing to know something, and it's completely a different thing to be able to break it down into very relatable terms for people who are not experts in that field to understand. And I would really like to appreciate you because that's what you have done, and you have done it perfectly. Thank you so much, Mr. Noah. Thank you, thank you, thank you. If Thank you. I'm seeing the emojis. Please, more emojis to show appreciation. Thank you, thank you, thank you so much. Please, if you have questions, this will be a good time for you. You can raise your hand or unmute yourself to ask your questions. We would like to hear from you. Thank you so much again, Mr. Noah.
Yeah, you're welcome.
Good evening,
Okay.
madam. Good evening, madam.
Good
Can I?
evening.
Yeah, I'd like
Introduce
to thank
yourself
the.
and ask your questions.
I'd
We can
like
hear
to.
you.
Yeah, I'd like to thank the speaker for the insightful presentation. But I have a question for Nigerian students that are looking at building softwares. What kind of advice will you give them? Practical advice on how they can develop good software that will be globally appreciated. Thank you.
Yeah, that's a very good question. And honestly, it's about the foundation. What I would say is start small, think big. I mean, let that always be your motto. I mean, it's tempting to want to build something, big right out of the gate. But the best way to build something globally appreciated is to start small. So focus on solving a specific problem or creating a niche product that you can scale over time. So focus on solving issues that your local community or a specific market faces. Once you have something valuable, you can expand its reach. It's also very important to master the fundamentals. So before diving into complex projects, it's essential to get comfortable with the basics of programming, data structures, algorithms, understanding how computers work, and how code interacts with data will help that strong foundation. And that's why I like analogies, because everything we do in software, we have always seen it in our lifetime. Everyone has experienced it one way or the other. So it's always good to analyze that way. Take courses, participate in coding challenges, practice consistently, embrace artificial intelligence as well, because it's really helping. It helps to, shed more light into certain difficult, complex areas. So, and also, yeah, collaborate and build a portfolio. So collaboration is key. Participate in open source projects, contributes to coding communities, or find like-minded people to build software together. Building a portfolio will be very essential as we move on into this in the coming years, really, because that portfolio will continue to speak for itself. So you can build portfolio through GitHub or through even your own website. Just show the world what you have built. And then again, it's always very important, because now information is key. Information is also very heavy these days. Lots of information everywhere. So, and that's why user experience is very important. People will only interact with your products if the user experience is good. So a beautiful product with a poor user experience is rarely successful. So even if your software is technically impressive, if it's hard to use, people won't appreciate it. I mean, so focus on user-centered design and usability. Test your products, listen to feedback, and continuously improve them. Yeah.
Thank you so much again, Mr. Noah. Thank you. Before we continue in the question and answer phase, please, this is the Association for the Advancement of Artificial Intelligence Nigerian chapter. Please follow us on Instagram, on Facebook, on TikTok, on X. No, we're not on TikTok, on X and on YouTube. If you enjoyed this session and you like to see more of this, please make sure that you follow us on our social media platform. Yeah, LinkedIn too. I forgot to say that. LinkedIn. Please ensure to follow us on all our social media handles. There are some questions in the comment section, so I'll just read it out in the live
Mhm.
chat rather. This person said, "Sir, what is API?"
Okay. Yeah. Good question. Uh, API is okay. So it's called Application Programming Interface. So it's like a bridge that allows two software systems to communicate with each other. So here's an easy analogy. Imagine you're at a restaurant and the customer, I think I mentioned something like that in the presentation, you know. So the customer is looking at the menu and he's saying, oh, this is the request. And then you tell the waiter what you would like to order. The waiter takes your order to the kitchen, which is like the back end system, and then brings your food back to you, right? That's the response. So you yourself, you never had to go into the kitchen yourself. but you still got your meal, right? So by following the waiter's process. So in the tech world, the customer are like the user or system that wants information or functionality. So the API is like the waiter in between that takes your request to the server and brings back the response. So, and then we also have server system, which is like where the real processing happens. It's like the kitchen where food is cooked. So an API defines a set of rules, how different software systems interact and how it allows them to exchange data or commands like or the get, requesting data, the post, the send, the put, the updating data, the delete, all of those methodologies. Yeah, I hope that answers that.
Okay. Precious, please indicate in the live chat if you okay. She said yes. The next question here is: what of a student who wants to study systems engineering? What should be his or her basics?
Hmm. Good question. Yeah. So, uh, basic software engineering, basic foundation. I would say that mathematics and problem solving is good. So I mean, system engineering is all about problem solving at a large scale. So strong math skill are really important. Um, I studied electrical engineering, and right from my early days, my math I've been very good. I still remember things I did in linear algebra, understanding system models, and it helps in understanding system models and transformations. Uh, Calculus, I did in my first degree, uh, which is very important in analyzing systems that change over time, like in control systems and all of that. So those things really help. And then understanding basic computer science also, at least try to understand one programming language thoroughly, maybe Python or C++. They can actually help in automating tasks. And the good thing is that artificial intelligence is helping also these days. You can learn a lot of stuff, a lot, through AI, through ChatGPT. All right. So, I mean, gone are those days where you have to, find a mentor or find someone, who is deep in that field to teach you or to tutor you. You can do self-learning now. You can participate in code challenge. AI will check your code and review it and tell you where you missed things. So it just requires a little bit of curiosity these days. All right. So understanding those basics up, and then how operating system works, how managing hardware, memory, and processes, all of those things. And then, yeah, those are some of and then basic engineering principles like being able to analyze things from other perspectives, looking at how things work in one domain and then being able to relate it. I mean, in software engineering as well. So those are some of the ways to get it done. Yeah.
Thank you very much. There's
And
another
one more
question.
thing,
Okay.
school projects, get involved in projects. So, I mean, in school projects or personal projects, just get involved in, that will help you to apply some of these system engineering concepts, build real systems, that will give you practical experience and deepen your understanding.
Thank you so much, sir. Also, please ensure you check out our website, which is triple-ai.org.ng. It is aai.org.ng. Please check out our website for more programs like this that will be coming up in the future. And you can send us an email for things you would like to learn about software development, artificial intelligence, tech in general. You can send us an email at info@aai.org.ng. Okay, so the next question here says, How can software technology help Nigeria INEC transmit elections results in real time? In real time, what advice do you have for INEC Nigeria, sir?
That looks like a trap. But it's a fantastic question anyway. Okay. Yeah. So I mean, I wouldn't speak particular to INEC, you know. I'll just speak particularly to, I'll just speak generally, how it works in terms of collecting real-time data. I mean, and this can be used anywhere in any election or in any situation. It's not just directed to INEC or whatsoever. So yeah, so in terms of real-time data collection, some of the things that helps is mobile apps help, for data collection. It also helps for GPS location tracking. So I mean, one way is to use GPS to verify the location of where things are happening, and then of course we have cloud-based infrastructure that helps to secure data. So, I mean, you collect data from a particular location, it can actually go into, that cloud server where it's secured. So even if there are large volumes of, things being uploaded at once, that capacity is there. So to prevent crashes and all of those things. And then encryption also, sometimes when you chat on WhatsApp, they tell you, oh, your communication are encrypted, right? So yeah, so some sort of end-to-end encryption also helps to avoid data tampering. And then we have new technology also, things like blockchain helps as well for transparency. So, and then you would also discover that when you are using your banking application, when you want to do transfers, you see authentication, multi-factor authentication. It will tell you, it will request for OTPs and all of that. So these are kind of like ways to verify that it is you. All right. So yeah, the multi-factor authentication helps in those situations too. And then yeah, it's also very important to test, because there is a problem we have in software engineering. You deploy a solution, all right, but and then when you deploy a solution, by the time that solution is now used, it crashes or it experience some sort of issues. Why? Because at the time when you deployed it, there was no load connected, no users. Right now, real users are using it. It's giving problems. It's crashing. So there's something called load testing. Okay, so it's always very important to do load testing. Before the real activity, test it. And the good thing is that the API technology I was talking about is also one of the ways to actually make things like this happen, because with APIs, you can simulate real data. All right. You can call in a service that say, okay, bring me 50,000 fake people from there. Let's test this thing, through APIs. You just call that service, and then they load test the application. So that's one thing APIs have to do. You don't have to find those 50 people yourself or find those things. You just call a service that is already offering that kind of package, through API. And then they come and then they test it, automated test. And so those are some of the ways to deal with stuff like this to avoid problems.
Thank you. Thank you, Mr. Noah. I'm glad you escaped the trap. Okay, another question here says, how do I translate these into real software building? I found the approach very interesting and engaging.
Yeah. So it's I mean, it's always about following concepts, best practices. And I'll say you need to come up with a clear plan first. So you need to It's just like having a plan. Before you build a house, you need to have a plan, right? So come up with a plan, break the project into smaller manageable tasks. Setting up the front end, the back end, the APIs, the database, creating a roadmap, a timeline, to delivery. And then you have to design the user experience. There's something called in design systems, there's something called user stories. So it's like highlighting user scenarios of how your app will be used. So you have to think about who will be using the app and what their needs are. Like, oh, okay, so, and that will influence the decisions around the user experience design, and then how atomic design comes in there. So tools like Figma, Sketch, they are used to design the user interface before diving into the coding. So, I mean, you need to follow these principles, right? And then the atomic design principle I mentioned, start with atoms, molecules, organisms, and all of that, and then use frameworks like React, to create reusable components. And then it's also very important to set up the backend. The backend is also very important. And these are how scalable applications are built. Yeah. So, I mean, backend is just like a house that needs a solid foundation. You need to have that, fantastic planning. You need to set up a database server. You need to choose a backend framework that works. One of the backend frameworks is Node.js. So it's just so just think about how data will flow in your app, just like plumbing in a house. It includes managing user authentication, passwords, sessions, and structuring how your application interacts with the database. So yeah, that's how you get it done. And then APIs. Just follow some of the principles mentioned in this training. Yeah.
Okay, do we have any more questions? You can unmute your microphone to ask questions. You don't necessarily have to type it. This session is being recorded and it will be shared on our YouTube channel. So an email, when it's uploaded on our YouTube channel, an email will be sent to everyone who registered for this program so that you can always catch a replay. Um, Mr. Noah, do you have like maybe a LinkedIn profile where people can reach out to you for
Yeah,
more?
sure. I'll share that with you, and then you can.
Okay, okay. Thank you, thank you. Do we have any more questions? I don't think we do. From my end, I can't see anything. Okay, that will be all. Thank you so much again, Mr. Noah. It was a very, very interesting session. As a business analyst, I learned a lot of what actually goes on at the back end in development and all of that. So thank you so much. Thank you everyone for joining us today. I hope this was worth your time. And I look forward to seeing you and meeting you in more of our events. Thank you.
Thank you. Thank you too.
All right, so I'll be ending the meeting now. Thank you.
Thank you, Ma.